So hello everyone, and thank you, Susanna, for the introduction. Um, so the webinar that we're going to have, the title of the webinar is Roadmap for the Future of Mechatronics and Robotics Engineering Education. So the abbreviation that we have for this is FoMRE. We haven't finalized on a pronunciation yet. I'm just going to call it FoMRE. In this webinar specifically, we are going to talk about outcomes of the first FoMRE workshop. My name is Nima Lotfi. I'm from Southern Illinois University, and I will be one of the presenters for today's webinar. So here's an outline of what we will be talking about today. First, I'm going to introduce the team that we have towards this effort that we've started. Then we are going to focus on the first FoMRE workshop that we held back in September in conjunction with Dynamic Systems and Control Conference in Atlanta. I'm going to talk about what went on in that workshop, what we learned from the workshop, in order to go forward, what are some of our plans? So that will be the topics in the roadmap, the third conversation topic that I'll be talking about, and what is it that we are planning on doing. And for this section, we would love to hear your feedback, what you think, what you suggest, and we would love more participation and engagement. All right, so first introduction. The team that I am fortunate to be a part of this effort to shape the future of mechatronics and robotics engineering is composed of Dr. Gennert from Worcester Polytechnic Institute, Dr. James Mynderse from Lawrence Tech University, myself, and Dr. Vikram Kapila from New York University. We also have Kwanzer as our industrial partner, and more specifically, Zuzana Fabusova and Tom Lee have been big supporters of our efforts. So we also have an advisory board. There is a good mixture of people from industry and also academia. So we're very fortunate to find these advisory board members who have been providing feedback and guidance in shaping our road towards the effort of future of mechatronics and robotics education. So vision. What vision did we have? Why did we want to start this effort? So our vision is that mechatronics and robotics engineering will become one of the most impactful disciplines in engineering, and to that end, by attracting diverse and innovative students who will graduate into professional engineers destined to design, develop, and implement transformative autonomous technologies that can be used to improve human health, safety, and welfare. Okay, so this is the vision that we have. We think this is the mechatronics and robotic engineering is the future. And you can see this in your everyday life by noticing smarter appliances, a smarter system in your everyday life. So what were some of our long-term goals? We wanted, so we started this initial core, but we wanted to expand this. We wanted to create a diverse and inclusive community of not only but instructors in community colleges and even K-12 institutions, students, industry professionals, and to be able to define what should be the knowledge base for mechatronics and robotics engineering, electrical engineering, computer science, or mechanical engineering. These are well-established disciplines. That's not necessarily the case for MRE. MRE is a fairly recent engineering discipline, and from university to university, there is not a set knowledge base for MRE. So that was another one of our long-term goals. Achieve recognition. So MRE, the universities are starting to pick up MRE as a distinct engineering discipline. But our goal was, our goal was to help with this, help increase the recognition, help with adoption. A lot of universities, a lot of professors would like to have such an engineering discipline, but they have a lot of hurdles. So how can experiences from other universities help with adoption of courses, curricula, and even engineering degree programs? So the approach that we had in mind was to conduct workshops in technical conferences that I'm going to talk about. We've already conducted the first one, and we will have a few more that I'll talk about later on. And we also wanted another one of our approaches was holding online webinars similar to the one that we have right now. This webinar series started since last year. Last year, we mainly focused on success stories from well-established mechatronics and robotics engineering disciplines. But this year, we are trying to bring the webinars in line with what we are aiming to achieve towards the future of mechatronics and robotics. We were very fortunate that National Science Foundation graciously provided us with some funding to support participants to our workshops, and also our industrial sponsor, Quanzer. They've helped with supporting participants and also various aspects of this effort, and we are very grateful for them. So the next topic that I'm going to talk about is our first workshop that we held 2 months ago, and I want to talk briefly about what happened in that workshop. So in this part, I'm going to I will be presenting along with my colleagues for different parts of it. So the outcomes that we had in mind for the workshop was standardized components, outlines, experiments, assignments. Once again, MR set and agreed upon group of components that for mechatronics and robotics engineering. Sharing success stories. There are some universities around the world who have had great success with mechatronics and robotics. Sharing these would help with adoption by new faculty, new universities. Involve other universities, involve colleges and universities which are not necessarily well known, but the outcome that we were looking for was to involve a broad range of universities. Partner with professional societies to spread the word, to increase engagement. Prepare faculty to teach mechatronics and robotics. And in line with our long-term goals, foster a diverse and inclusive community of students, educators, and industrial professionals. So, workshop participation. We had an online application form for participation workshop. We received about 81 applications, and the majority of these applications were from academia, but we also had some students, postdocs, and also some industry professionals. We were able to provide financial support to 18 applicants, and our industrial partner, Quanzer, they provided an additional 4. But despite the number of the travel support that was provided, we saw around 30 people attending the workshop, which was very exciting. So in regards to demographics and where the participants were from, they were mainly from United States, but we had a few from India, Pakistan, and I think Syria. In United States, interestingly, the majority of the applications were from the east part of the country, but it was kind of spread all over the United States. In regards to format, what happened in the workshop? So we started with some introductions. But after that, the main portion of the workshops were some interactive sessions. So the participants were divided into smaller groups based on their own interests. And in the first interactive sessions, we addressed these problems, these topics that we thought are important for shaping the future of mechatronics and robotics engineering. These interactive sessions turned out to be very rich and constructive, and we actually ran over the time that we had originally in mind, but we ended the interactive session with a report out. We had a small break, and then we had our second interactive sessions, which again were composed of very interesting, constructive conversations, and that ended with another summary. And we didn't even have time for a second break. But this is how the workshop actually was formatted, or the format that we had in mind. So um, after the workshop, we had taken minutes. Each interactive session had a minute taker, a moderator, and a reporter. And after the workshop, we reviewed those minutes. We reviewed what went on in each of the interactive sessions. We discussed about these, and we wanted to bring the summary of these interactive sessions to a broader audience. That's one of the reasons that we are holding this webinar. And next, I am going to talk about the summaries of the interactive sessions that I was involved in. And after me, my colleagues will take over and talk about the interactive sessions that they were a part of. So the first interactive session that I was involved in was named Advanced and Open Source Platform. So what I had in mind, I was basically thinking of standardizing, having a standard set of platforms, experimental platforms for mechatronics and robotics engineering. It could, the platform can be defined in terms of software or hardware. And but one of the big questions that we had for this first interactive session was concentration. So there are different levels of courses in a mechatronics and robotics engineering degree program. How should these platforms look like for a freshman course, for a course in controls, in robotics, for a mechatronic system design? Then another topic that we discussed was application. What should be the main focus of these platforms? Should they look at basic electronic and electrical components and circuits? Should they be more focused on data acquisition, or should they be more application oriented, robots, drones, stuff like that? So, and obviously, what kind of platforms are recommended, software-wise, hardware-wise? So these were the main conversation topics that we went in with for the interactive session, but actually these are the summaries of what we talked about. So as I mentioned, the conversations were very constructive, very informative. But one of the things that we first needed to clarify was hardware versus software, because this concept of advanced and open source platforms can include both. So we have hardware platforms from companies such as Quanzer, National Instruments, that are very robust, very well designed. On the other hand, we have hardware platforms like more open source hardware platforms such as Arduino, Raspberry Pi, is still very well designed. However, in order to build a more complete system, a lot of design and manual labor needs to go into these. On the other hand, on the software side, we have software platforms such as Python, C, that's mainly used in open source platforms. But you could also use LabVIEW or MATLAB, which are more commercial software. So we did talk about these different platforms, the advantages and disadvantages that each of those has. But one thing that was very obvious from these conversations, one of the pros of obvious open source platforms is lower cost. You can buy Arduino for $30 and you can't beat that price. So the lower cost is definitely one of the attractive aspects of open source platforms. And utilizing open source platform can actually provide a very rich learning experience for students. But on the other hand, it is going to take a lot of effort, a lot of design and tweak and troubleshooting in order to get a well-designed system and operational system. So for that, you would need, and I'm talking this from first-hand experience, you need students with good hands-on skills, students who are familiar or at least are provided some kind of guidance in order to develop these platforms. And one other topic that which was very interesting, a lot of people in the group shared this concern, was troubleshooting in regards to open source platform, both hardware and software, right? So you hear about Arduino, Raspberry Pi, Python, or C++ every day. The problem is it doesn't seem to be a unified resource that can help with troubleshooting in regards to, let's say, Python, or even platform based on Linux. There seems to be a lot of answers seem to be in forums, and forums can be very noisy, and they're not necessarily developed by faculty members. Some of them, although very valuable, some of them are just hobbyists or people from different disciplines, different focuses that contribute to those forums. And at times it can get frustrating to go through forums conversation trying to find an answer. So lack of a solid resource, a solid reference that can be referred to in order to troubleshoot these systems was a common concern. So following that, a lot of people teaching mechatronics and robotics engineering seem to be coming from controls background, either in mechanical or electrical engineering. And unless they've been unless they were exposed to these open source platforms, they are really not going to have a lot of training in this regard. So one other concern that we did talk about was how can we provide opportunities in order to train educators in this field. Another concern, another conversation topic that we talk about was control implementation. In control courses, we do talk about very advanced control algorithms. But it seems to be very difficult, and there seems to be not a lot of resources in regards to implementing these advanced algorithms on board open source platforms. So that was another challenge that using open source platforms presents. On the other hand, commercial products are very well designed for implementing such platforms. And one suggestion, one conversation that we did have was to utilize a commercially available product, modify it, and incorporate an open source hardware board like an Arduino, or degrade the performance of a commercial system with aiming to teach the students challenges that they might have with these systems. And another another topic that we talked about was the need for a repository. All universities offering such degree programs and such courses, they have come up with experimental platform, both open source and also commercially available. There are numerous companies building such platforms. But there seems to be lack of unity. There isn't a certain online resource that educators can refer to find such a platform. So this was another area that we talked about, and it seemed to be concerning for MRE educators. So again, a lot of conversations went on in this interactive session. all of them very constructive, and but these are just some these were just some questions, some challenges, and we didn't necessarily come up with solutions. We talked about some possible solutions, and I'm going to talk about more about these in our roadmap. But in order to achieve those, we need engagement. We need community members. We need to expand our community and engage our community members in order to kind of streamline the needs that our educators have. And in following the community building, that was the second interactive session that I was involved in. How can we expand our community to some professional and also to some professional and also technical communities? How can we expand our community, and how can we increase the engagement? We talked about mechatronicseducation.org. This is an online resource that we have started in the past 2 years, and I'm going to talk about that a little bit more. But increasing engagement, that's another important piece. We need people to take part in conversations that we have in the forum in this website. We have a repository. We need volunteers to help us gather these different online materials in regards to mechatronics and robotics engineering. And one other concern that became very apparent was that, yeah, a lot of professors have done very valuable efforts towards mechatronics and robotics engineering education. But if they were to participate in this effort that we have here, what would be the return of investment? What would they get in return to participating in this? So that was another concern that seemed to be common among the participants. And of course, attracting external funding in order to increase audience, increase engagement. This is something that could help. And increasing diversity, that's another thing that we need: community participation, personal references, in order to make sure that underrepresented groups, universities, minorities are included. So these were some of the conversation topics that we had in the second interactive session, and I'm going to talk about this in our roadmap. But now, and I think I talked a lot, I'm going to pass it over to Dr. Kapila so that he can say a few words about the interactive sessions that he was involved in.
Dr. Kapila, if you can please unmute yourself.
Sorry, am I good now?
Yes.
Okay, sorry about that. Once again, this is Vikram Kapila. Good afternoon, everybody. So before the workshop, we had organized a couple of the strawman documents to help guide the discussion during the interactive sessions. And for the mechatronics education knowledge base, I had organized the different knowledge components in these three baskets, if you will. The disciplinary knowledge, or the foundational knowledge that one needs to be able to study mechatronics, the interdisciplinary knowledge that one needs, and then also some people call it soft skills. I much rather call it a professional skill. But in disciplinary knowledge, we were concerned about the kinds of math and physics that somebody would need, as well as the traditional engineering foundational knowledge. And then in the interdisciplinary knowledge, we were concerned about the interdisciplinary components, excuse me. interdisciplinary components from mechatronics, and then finally the professional skills. Could you go next, Nima? So during the workshop, the discussions were very informative, and we were able to reorganize what we had proposed in the Strawman document in the following manner. So first, all of the elements of the interactive knowledge base actually are the ones that go into the mechatronic core. And for the mechatronic core, we agreed that this should include the fundamental knowledge and practical experiences with elements known as sense, think, act, communicate, that we without any problems stole from Quansar, as they had an introductory presentation where they had organized various components of the mechatronic thinking into these buckets of sense, think, act, and communicate. So basically anything to do with sensing, anything to do with communication or thinking, computing or thinking, and then actuation, and things like data acquisition, I2E, SPI, the different communication protocols. We said that these should be the core of the mechatronic. Other ancillary items were also discussed. What kind of programming languages should be included in the mechatronic core? What kind of embedded computing aspects should be dealt with? There was a big push made to include human-machine interaction aspect within the mechatronic core, and I think that would be very useful. Then what we had originally called as the fundamentals for the mechatronics, now we are calling that prerequisite knowledge base, and this is essentially the science, math, and engineering fundamentals. So we agreed that most of the physics and math courses should be kept as in our undergraduate curricula, with perhaps a minor tinkering. Maybe you don't need a modern physics course, or maybe you don't need a chemistry course. Maybe you make some free electives for science. Maybe somebody needs biology to be able to do biomimicry, or maybe somebody can do statistics for machine learning, and that would be fine as well. And then it was suggested that instead of having many engineering fundamental courses as standalone courses, maybe some could be combined as statics and dynamics combined in a single course as engineering mechanics, and perhaps electricity and electronics could also be combined in the similar manner. It was agreed that dynamic modeling and feedback control should be kept as prerequisites. These are engineering fundamentals, and if the students don't have the basics of modeling and feedback control, anything they do within the mechatronics core would not be following a systematic approach, but rather they would be doing more trial and error, which is not very good. There were some other miscellaneous items discussed. What kind of freshman experience one ought to create that engenders a need for learning about mechatronics. It was also suggested that the curriculum leave out maybe 15 to 18 credits of free electives, which could allow students in mechatronics, if they wanted to specialize within a discipline such as mechanical or electrical or computer engineering, they could take a minor in one of those standard disciplines, or maybe they would do more experiential learning. Perhaps maybe they will participate in research or credit-based internships to maintain a futuristic outlook. It was also suggested that we consider courses in computer vision, machine learning, as well as artificial intelligence. The next slide, please. My second interactive session focused on reducing barriers to adoption, and once again, we had a Strawman document that talked about how faculty might face a lot of burden without having a agreed curriculum. Maybe they don't have curriculum material that has been well developed, or it's only focused on the local interest and expertise. Curriculum development requires a lot of time commitment and effort. Maybe the lab has a lot of challenges in terms of space, experimental apparatus, as Nima talked about. The technology is rapidly evolving. You do something with one platform today, 5 years from now, it would be completely outdated. Which also means that on an ongoing basis, you have to invest in the lab and invest in the training of the lab assistants with a new tool. And nonetheless, what we do in our own academic labs, we almost always seem to be lagging a little bit behind what happens in the industry in terms of the standards and tools, but also the scale. Often we do things at a smaller scale than what might be done in the industry. Next slide, please. So starting with that straw man, during the interactive session, these were the barriers and solutions that were pulled out. Obviously, everybody indicated that there was a lot of constraint in terms of the time that is available to develop new curricula. The funding is not always there. Universities may be tight in space, especially in the urban areas. And then there are not always sufficient faculty resources available. There may not also be a buy-in from traditional engineering department because remember, in order to create a new bachelor's program or a graduate program in mechatronics or robotics, you don't start by hiring faculty from day one. Essentially, you have to build some buy-in in the existing departments, create some interest, and then eventually maybe you can hire new faculty. But as you try to create that buy-in, often the existing departments might have a perception that they have to divert from their own core activities into these new areas, and they may not always be willing to do that. There is also a lack of faculty resources in terms of faculty not necessarily having their own training and education in interdisciplinary fields. Maybe they are not very well trained. They don't feel comfortable stepping outside their zone of knowledge. And then also there is even now a lack of commonly agreed knowledge base and educational material for the discipline of mechatronics. So some possible solutions that were proposed, that instead of creating full-fledged programs and degrees in mechatronics, maybe those who are intending to follow through, maybe they can start out a little small. Maybe they start by piloting a course or two, or even try to start out a minor and then assess the student engagement and look at the career outcomes of those students based on the pilots that you have created. And often showing those successes could provide further ammunition as you try to grow from a couple of courses or a minor to a full-fledged program. Even though the traditional engineering departments might not be willing to buy into an interdisciplinary degree program from the beginning, maybe that's not what we should even ask about. And then, in a stealth mode, just build alliances with these departments. Let them see what you are able to achieve in your own academic program with a couple of courses, and how students are responding to those courses. As you build these alliances, those colleagues would hopefully become champions at the right moment when you start building the momentum for the full-fledged undergraduate or graduate program. If your faculty colleagues don't have the knowledge base for these interdisciplinary programs, maybe you can start doing some collaborative activities with them, even for teaching. Maybe you can create a module for a feedback control course where they are able to use a mechatronic device to show and engage students in some experimental activities. Maybe their doctoral students can rely on your experience to conduct some research that makes use of your knowledge in mechatronics and robotics. And through activities such as workshops and conferences and forums and so on, develop your own leadership potential so that within your own community, at your own school, you will be taken seriously when the time comes for you to propose and champion such a program. So I think with that, I'll pass on the baton to Michael, who would talk about his two themes.
Well, thank you very much, Vikram, and thanks, Nima, for getting us to this point. I'm going to talk about the about two of our sessions. One was on the robotics education knowledge base, and the second one is on accreditation issues. So let's start with the robotics education knowledge base, which is actually quite similar to the mechatronics knowledge base, and the two really are very similar, just a little different perspectives. A lot of that is historical, and in fact, the two I think have quite converged. All right, so on the one hand, we have knowledge within the traditional disciplines. There's math and physics as the foundations, and then we have computer science and computer engineering, electrical and mechanical engineering. And then these get combined to form what really is the interdisciplinary knowledge core for robotics, and that you can look at that in the components or the robotic subsystems. So, for example, there's actuation. Now, each of these will take elements of computer science, engineering, electrical, mechanical. So, to do actuation, you have to understand both the mechanics and the electronics that drive that, and the software that's going to make that happen. Likewise, for sensing, you have to worry about what the sensor physically is and the mechanics of that, especially if it's, say, a force sensor or pressure sensor, and then how you convert that physical quantity into an electrical signal you can then sample and then compute with that. So these all integrate. So integration is a huge part of robotics, integrating these actuation and sensing systems. You can think of this as being a kind of systems engineering, and you really have to take a disciplined approach and think about what are the requirements you're trying to satisfy, what are the needs, and how those turn into constraints on the design, and then the actual design implementation, and then you have to test in the other order. There are many applications, of course, from medicine, defense, manufacturing, entertainment, safety, and so on. And we can look at advanced topics, advanced things like soft robotics, locomotion, navigation, vision, haptics, and human-robot interaction. And in some ways, as important as the quote hard skills are the professional skills. I don't want to call them soft skills. That's a common term, though. But really, this is what makes our graduates able to function effectively as part of a team, and makes them valuable both employees and leaders. We have, of course, the personal skills. How will they listen? How will they interact with folks? Their ability to be empathic and understand their coworkers. The mindset. Are they thinking like entrepreneurs? Are they being bold and courageous in their thinking and their designs? And the last of these is society and ethics. We understand that robotics and mechatronics are immensely powerful technologies that have the potential to severely disrupt our current ways of living and working. And it's imperative that our graduates understand the implications of what they do on society. And besides that, they have to understand the sense of professional ethics and what their accountability is as robotics and mechatronics professionals. Next slide, please. Drilling down a little bit within these areas, there's some topics that we found were quite important, and there was pretty much agreement on a lot of this. For math and physics, students have to understand, well, first off, geometry, how things fit together, coordinate systems and transformations, calculus, DFQs, linear algebra, stats and probability, and kinematics. From that, they can use that as a foundation to go into sort of general engineering, the components from mechanical, electrical, computer science that they need, such as noise and signals, how to do acquisition, instrumentation and measurement, controls, just like Vikram mentioned. That's a very important component here. Material strength, machine design, CAD simulation, architecture, embedded software, and programming. And perhaps we don't need to have every one of these, but that's a good foundation for doing more advanced robotics. And then specific things you might encounter in a curriculum would be industrial robot manipulation, robot navigation, sensing, both tactile and vision, even could include sonar in that, actuation, understanding motors, linear actuators, perhaps soft robotic actuation, and motion planning, excuse me, and navigation, guidance are all topics you could include here. There are many possible electives one could include in robotics education. Human computer and human robot interaction are increasingly important. AI and intelligent decision making and learning, and then cognition in general make for good topics to include. And then society and ethics, we also need to understand the philosophy to understand how robots and humans should behave together. And then there are legal issues, and a professional ought to have a sense of what the legal concerns are involving robotics. And then we agreed that it benefits students immensely if they have some practical work experience before they graduate through internships or co-ops or summer jobs where they can use what they've learned so far to see how that works in companies. Next slide, please. Our second session was on accreditation, and we discussed, first off, why to get accreditation and the benefits and costs of that. On the benefit side, if you're going to have a respected engineering program, it ought to be accredited by ABET. And the cost, well, there is a cost in terms of money to get accredited, but even more than that, there's a time involved in having people work on self-studies, accreditation visits, and the entire accreditation process. So let's look at ABET, which accredits engineering and computer science and technology programs in the United States and abroad. There are 8 categories of criteria. And then there are general criteria that apply to any engineering program. and specific criteria that apply to specific disciplines. On the general criteria, these involve, first off, the students, making sure they can get through the program and that they're well advised. Then we have the program educational objectives, what students should be able to attain within a few years of graduation. These are not things that you measure. These are loftier goals, such as work as professionals, go to graduate school, start companies, things like that. Student outcomes are the specific things that you can measure. What students should be able to do at the time of graduation, what's their knowledge and skills. Next is the continuous improvement criterion. One has to have in place a process for assessing how well students perform against those outcomes, evaluating that against some criteria, and then improving what one does so that students can better achieve those outcomes. That process is very important for accreditation. It's probably where most programs get in trouble, when they don't close the loop and re-examine how they do stuff. Okay. Next set of criteria involve, go back, thank you. Involve the curriculum and what's the engineering, science, and math components of that curriculum. Then there's the faculty criteria. Are the faculty adequately prepared? Do they have enough time to develop? Are they appropriately resourced? Is their workload appropriate? Then there's the facilities. Does that enhance and enable student learning? Are they up to date? Do they have modern tools and instruments? And finally, there's support from the institution. Does the program have the resources that it needs to function appropriately? All right. Now, beyond the general criteria, there are specific criteria. So, for example, electrical engineering has its set, mechanical has its set, biomedical, and so on. There are none for robotics and mechatronics. So one would be accredited under what's called general criteria, and there are no specific criteria there. But if there were to be a set, who would lead that development? What would be the lead societies? And then should there be one set for both mechatronics and robotics, or two different set of criteria? What would the curriculum look like? What are the faculty needs in those areas? Okay, so then we go from there. Let's go to the next slide and talk about some outcomes from this. So in the United States, we have ABET. In Canada, it's CEAB, and they function relatively similarly. And again, one needs to be accredited for any engineering program, both to ensure program quality, and if one's in a school or college that has engineering programs, one would have to be accredited to have standing. And some students must attend accredited programs. For example, students in ROTC engineering programs have to go to an accredited program. You can get useful feedback from program evaluation, and that's one of the benefits of it. You get an external view of the program from top to bottom against those criteria. That feedback is given to the program and the administration, the deans, provost, and president. I was just on an accreditation visit as an ABET evaluator, and I would say that the department head that we talked to and the dean and provost really welcomed our input and evaluation. Any program in mechatronics and robotics should pretty easily meet the ABET general criteria. There's a certain requirement for math, science and engineering, science and design, and it'd be pretty hard to design a program that didn't meet that. And there's breadth and depth as well. And again, those are pretty easy to meet. And more important than the course content is that continuous improvement process. That is where most programs get dinged. As I mentioned, MRE programs can get accredited under general engineering, and maybe we'll have some MRE specific criteria, but we don't have any quite yet. The consensus of our session was it's better to have one set of MRE criteria rather than two distinct ones for mechatronics and robotics. They're so similar that you might have electives that differ, but I think the core knowledge base of the two is 95% the same. And having criteria specific to mechatronics and robotics would help standardize the curricula. So we know that there's some uncertainty over what ought to be in mechatronics and robotics programs. Well, accreditation with specific criteria would help to nail down an agreed upon knowledge base that one would have to cover. So that would be very helpful for standardization. But one doesn't have to have an accredited program. Other alternatives are to have degree options or concentrations or specializations or minors within some other discipline. In that case, you could fit under that umbrella. The drawback, though, is that concentration or option, whatever it is, would have to meet the criteria for the discipline as well as the mechatronics and robotics content. So that might be broader than you need. So, for example, would you want to require every robotics engineer to understand, let's say, thermal fluids? Well, you'd have to under mechanical, but maybe that's not as important for mechatronics and robotics. Or under computer science, would you really want every roboticist to understand Turing complexity, for example? Right. So those kind of things are worth discussing. And with that, I'm going to hand this over to James.
Thank you, Mike. So the two sessions that I was responsible for were project-based learning and preparation to teach in MRE. So for project-based learning, these are the bullet points that we put on the handout we provided as a starting place for our discussion. So we were initially thinking about different types of projects, whether they would be big or small or in class or mostly out of class, whether you're designing or testing or anything in there. There's a range of different ways that you could do projects, and there's a range of different courses that might benefit from doing project-based learning. Personally, I say all courses, but we wanted to include a couple of items there just to start the discussion. But any project-based learning runs into some challenges as well. Things like the scheduling of it. If you are doing a project, you usually need to allocate time for that, and that's time that you're not lecturing, that's time that you're not doing other in-class activities, and so you do have to work your schedule around that. When you do projects, it takes a heck of a lot of time for the faculty to prepare as well as for the students to do, and so you have to make sure you're not burdening either one excessively to meet the needs of the project. There's also a lot of uncertainty that goes into it. This is one that I actually find really interesting, is that when you're running a project, you don't necessarily have the right answer. And you're more guiding the student than you are lecturing to the student. And so I find that really interesting that the students are coming up with great questions and I don't have the answer, and I have to help them find the right answer, but I don't know what it's going to be. There's also potentially cost and questions about availability of lab space. If you need lab space, how does that work with the rest of your scheduling? So Nima, you want to switch to the next slide there? All right, so we had a nice discussion. This was the first session, so frankly, the first part of our discussion was just meeting the other participants in the group and talking about what our prior experience was in terms of teaching mechatronics and robotics. And it turned out that everybody at my table had prior experience running projects, and we all generally agreed that we saw an increase in student motivation, we saw an increase in student learning. It was generally a good thing. We also had two, I'm going to call them future faculty, two folks that were nearly done with their doctoral programs, and we're not really sure where they were going, but probably going to be teaching. And so it was nice to get their input as well, and hopefully for our future workshops, we'll continue to get future faculty involved as well as current faculty. So when we were talking about types of projects, we had some folks from engineering and also some folks from engineering technology. We had some specific examples of using thematically connected projects, tying different student projects to the same area, automotive or agriculture or biological. But one of the problems that came in was that most of us had tried at some point a multidisciplinary project where you had students from different backgrounds. And the students from different backgrounds, because they're coming from different backgrounds, as Mike was talking about with accreditation, you run into questions of what do they have in terms of their background knowledge, and can they get the things that the other students have? So if you've got a mechanical engineer and an electrical engineer, do you naturally split up based on their strengths? Do you encourage them to work on some portion of the project that they're not strong in? But merging those background knowledge sets can be a challenge. It's not impossible. It certainly can help the students, but it is a challenge. And one of the biggest discussion points we had was talking about assessment. How do you go about assessing the student learning? How do you go about assessing the success of the project? There were certainly some participants that were interested in a holistic assessment versus some that were looking at what did the individual students do. And there was a great suggestion of having a review board, essentially like a Shark Tank situation, of faculty and industrial advisors, specifically with the industrial sponsored projects, or the projects maybe that are not financially supported by industry but are coming from an industry background, getting the industry folks in there to help discuss the strengths and weaknesses of each of the student designs. But when you're dealing with stuff like that, there's often a need for sponsorship, for materials, for access, for information, and that can be a real challenge. It depends on where your university is. It depends on what relationships you already have, and that can be a challenge for a lot of faculty. Nima, can you move on to the next slide? Thank you. So the second one that I was dealing with was talking about preparation to teach MRE. So what we were talking about here is assuming that we're all good on the technical side, which I think because of things like ABET and the Canadian equivalent, that we're all coming out of all of our faculty are coming out of universities that are technically sound, and everybody's got the background that they need for the material. But then what about the classroom portion of it? I don't know that everybody is coming out with a preparation to actually be in the classroom. And we were talking about what have we done individually, what have we done as universities to make sure that our faculty are ready not just to present technical material, but to connect with students and to present it in a way that students are learning. So we talked about a little bit about what options there are in terms of training, what options we have taken advantage of in terms of training, and what we think people should be doing. Next slide, please. So it turned out that the group that I was talking to, almost everybody there had previously completed some manner of workshop or certification program on education. So I've got listed here some examples of what people had done. The National Effective Teaching Institute, the NSF STEM Fellows, the Keen Innovating Curriculum with Entrepreneurial Mindset workshops, and then there were several university-specific onboarding workshops. These were all good options. I did wonder whether the folks that were showing up for our workshop were self-selected as folks that would have participated in these, and I think maybe there's room to discuss how broadly these sorts of things are being done. But I think at the table we all agreed that active learning and the various techniques that go with active learning are very important, and we want to make sure that folks that are teaching MRE are prepared for those active learning techniques. And that's probably the biggest outcome from this was the discussion of how you facilitate the student in an active environment, how you facilitate the student in a problem-based environment, because there was a lot of carryover between the two discussions. So that's one of the things to focus on going forward. So I'll hand it back to Nima to carry on with our roadmap.
All right. Thank you all for your presentations. So I apologize for the time. We were originally planning on 1 hour, but we're a little bit over. So I'm going to quickly continue. And the next topic that we have here is roadmap. So what do we do next? So this first workshop provides us with a lot of nice outcomes with the burning questions that some faculty members have in mind and some solutions. Not as you've probably seen from the conversations, we didn't come up with all the solutions. We just discussed the topics, the challenges and issues that are there. So in short, we are going to continue workshops. We are going to hold webinars, and I'm going to talk about these a little more. We are going to write, we need to connect with professional and technical societies. We need to write grant proposals. We need to create online materials. And if you're interested in being a part of these, just get in touch. I have my email in the last slide, but we need community members' help to expand the community, engage, take part in publications, proposals, and so on. So in regards to workshop, we have proposed 3 more workshops, and so the second one is in Accra in May. Third one is Robotics Summit and Exposition, and fourth one is ASEE. So we have already submitted proposals for these workshops, and we are hopeful to have the proposal accepted and have other have the workshops in these conferences so that we can engage our previous community members and also newer members. Webinars. So for the fall semester, I think we will only have 1 more, but in spring we're going to have a lot more webinars. For the fall, early December, we will have Dr. Venkat Krovi from Clemson University. He's going to be our next presenter. And as I mentioned, we will have more webinars. So if there are topics, so all these topics that we talked about, if you feel like you can contribute to the community, if you feel like you have the answer to maybe some of these questions, just reach out, be a presenter in our webinar series. And we could all use the experiences that are that faculty members in different universities around the world have. So mechatronicseducation.org, I briefly talked about that before. So it's the website that we've had for the past 2 years. It provides an opportunity for the community members to get involved. It has a forum that you can actually start conversations. So if you go to this address up here, there is a button called New Discussions. So go there, start a new conversation. Or we already have conversation topics. I posted 2 in regards to the interactive sessions that I was involved in just last week. So if there are some burning questions in your mind, just go and ask them over there. Or you can even answer some of the questions that other people have posed over there. In this way, we can increase the engagement, we can expand community and find answers to some of these issues that we have discussed throughout this webinar. We also have a repository, online repository. So definitely, and these are all free. If you become a member, you just register for free and you can get access to all of these. We already have some information about well-established program, curricula, syllabi, student project ideas, workshop. So the previous webinars that we had last year, there are recordings, present slides for those webinars. We have recordings of the workshops, previous workshops that you can find on the repository. So a lot of valuable stuff, but we need more. So we need volunteers to collect these materials, to post them on the repository, because we don't want our website to be just another website in the ocean of internet, right? We want it to be active. We want it to attract community members and help with shaping the future of mechatronics and robotics engineering. Another important thing that we are definitely planning on doing, and this is, once again, we need your help, is outreach. How can we bring more people to increase diversity, increase inclusivity in our community? Society of Women Engineers, National Society of Black Engineers, Society of Hispanic Professional Engineers. If you have connections or if you're a member of these societies, please let us know. We would love to get in touch with them, spread the word about our upcoming events in these societies so that we can increase diversity. Technical societies, these could be great places to promote our efforts to increase engagement. We might even be able to attract some funding to hold different events, or to, for example, for teacher training. I know Dr. Kapila has done a lot of valuable trainings in the past, but we could continue that with more recent technologies that MRE educators need, and industry. So one of the main reasons we will be holding the workshop at Robotics Expo and Summit is because their main focus is industry, and we need people from industry to tell us about their exact needs. What is it that they are looking in their future employees? So again, I'm sure every university has an industry advisory board. So reach out to them, talk about this effort, and we would love to have them in our community. And if you know of other underrepresented minorities, universities, community colleges, or even high schools, K-12 institutions, we need these people in order to improve this field. So with that, I'm going to finish my presentation. Thank you again for your attention. And once again, I'm sorry if it ran a little bit longer. This is my email address right here. If you want to get involved in any form, please don't hesitate to contact me. I would love to see your emails about getting involved in the community and helping us reshape this field. So once again, thank you very much. And so it's supposed to be question and answer time, but we don't have a lot of time. So I'm gonna see if we can at least answer one question that was asked. So it was about accreditation, and it was about European universities. Mike, do you know if European universities can be accredited by these associations, ABET or the Canadian equivalent?
Yes, ABET is international, and they will gladly respond to a request for evaluation from any university anywhere. But they tend not to, from Europe.
Yeah, okay, okay.
Yeah.
Are there any other questions? So I'm going through these, what we have in the chat box. So please, if you have any questions, go ahead and post them in the chat window, and we'll be happy to answer those. So there's a question about getting involved. If I want to get involved, what do I need to do? Just send me an email. We can talk more. We could set a meeting about future steps, how you want to get involved as a webinar presenter, and writing papers, proposals. Just shoot me an email. Once again, this is my email, and we can talk more. All right, and there is one more question, but because of the time, I'm going to stop here. If you have, so I talked about the community and the website. Please go to the forum, post your questions there, and we will try to start the conversation over there. So once again, thank you very much for being part of this webinar, and I hope you've enjoyed it. I'm looking forward to further collaborations in the future. Thank you.
Thanks.